Hello, this is problem set number 2, problem 6. If deep-sea divers rise to the surface too quickly, nitrogen bubbles in their blood can expand and prove fatal. This phenomenon is known as the bends. If a scuba diver rises quickly from a depth of 25 meters in Lake Michigan, which is freshwater, what will be the volume at the surface of a nitrogen gas bubble that occupied 1 cubic millimeter in his blood at the lower depth? Does it seem that this difference is large enough to be a problem? Assume that the pressure difference is due to only the changing water pressure and not to any temperature difference. So the temperature remains the same. The initial and final temperature are the same. This assumption is reasonable since we are warm-blooded creatures. Okay, and we have a little drawing of our problem on the right with the scuba diver represented by the brown point, and it is 25 meters below the surface of the freshwater lake. Okay, so since I am given the initial volume of this nitrogen gas bubble, and I am to find the final volume once the diver rises to the top of the surface of the freshwater lake, I'm also given that temperature does not change, and I know that I'm looking at a single nitrogen gas bubble, okay? And so the amount of gas doesn't change. So based on those given information, I will use the ideal gas law in section 18.1. Okay. And that is PV equals nRT. Right? And this equation should be in your formula sheet if it isn't already. Let's just go through it real quick. So we know our temperature is, this is constant, right? Temperature is constant. And that's given right here, that there are no temperature differences. Okay. R, we know that's also a constant. Okay. And N is the amount of gas, right? And we are focusing on an N2 bubble, right? From beginning to end. So the amount of gas doesn't change. So this is also constant. N is constant. We'll have the same amount of moles of gas from initial to final. Okay, so I was given the initial volume right here, and I'm trying to find the final volume. So that's this guy, right? And as for pressure, that I'm going to have to find the initial and final pressure of, which I can do, and we will get to that. However, I just want to point out that this pressure in the ideal gas law is the absolute pressure, okay? So this is, P is absolute pressure. Or the true pressure, all right? Okay, so given that, now that we know that, we can say, let's mark some stuff. So initial scenario versus final scenario. Okay. So initial would be P1, my initial pressure, V1, which is given right here, is equal to nRT, right? And we know that this is constant. That's what we talked about right here. Temperature does not change. R is a constant, right? So that doesn't change. And we're still focused on the same nitrogen gas bubble from beginning to end, so the amount of gas doesn't change, so that's also a constant, okay? So these three things on the right side of the equation, they're constants. Okay? Okay, for the final scenario, we're going to have the final pressure and the final volume is equal to nRT. Right? And these just come from the ideal gas law. I'm just applying it to the initial and final scenarios. And the same thing for the final scenario, right? These three are constant because they don't change. So if this and this are constants, they're the same thing, that would mean that these guys are also equal, right? If these two are equal, then these two are equal, okay? So therefore, P1 V1 would be equal to P2 V2, right? That's initial pressure times initial volume. It would be equal to the final pressure times final volume for this N2 bubble that we're focused on. All right. Let's mark what we already know. We were given initial volume, right? Right there. So actually, let's write that down. We know V1 was equal to 1.0 cubic millimeter. Okay. And we know that we want to find the volume at the surface after the diver rises to the surface. So we are trying to look for V2, okay? So this guy is a given. This guy we're looking for. And let's find a way to solve for pressure. Initial pressure and final pressure. Okay? All right. So in order to find the initial pressure right here, when we're down here, the scuba diver is 25 meters under the surface of the freshwater lake, we could use the equation for hydrostatic pressure at a given depth, okay? So let's just put that here. So this is the formula for the hydrostatic pressure at a certain depth. Hydrostatic pressure and at, let's say, depth H, okay? This is just however far underneath the surface of the fluid you are at, which in this case is fresh water. So the formula for that is absolute pressure, right? Because that's what we need here. In order to use the ideal gas law, we need absolute pressure. So absolute pressure, or true pressure, is equal to the pressure at the surface plus the pressure due to the fluid at this depth right here of 25 meters. So that is rho GH, okay? And I'll just mark down what rho is. So rho is density of the fluid. G is gravity, okay? And H is depth, right? That's the given depth. And all these guys is a pressure due to fluid at depth H. Okay? Which we know in this problem, H is 25 meters right here. Okay? Oh, actually, I'll write that down too as a given. So H equals 25 meters. All right, and this guy right here, P naught, this is the pressure at the surface. Okay. And our surface in this case is right here, right? So in this case, at the surface, right here we have atmosphere. That would be the atmospheric pressure, right? Because this is in the atmosphere right there. Okay. So then we could find our the absolute pressure initially, right? So P1. And let's do that. I'll just write this down. This would be our true pressure or absolute pressure. Okay. And that is what we need, again, to use in the ideal gas law equation. Okay. So let's look for initial pressure. P1, right here, okay? So P1 would be equal to the pressure at the surface, this guy, which in our case is atmospheric pressure, right? Because in the surface, this is all atmospheric pressure that at the surface. So P naught is atmospheric pressure, okay? Plus density, rho, of fresh water. So fresh water density times gravity times the depth that we have, okay? Which we know right here. It's 25 meters, okay? So let's plug in our numbers. For atmospheric pressure, this might be a good thing to also have in your cheat sheet. But atmospheric pressure is equal to 1.01 times 10 to the 5 pascals, okay? I'll just put a red box around it because it might be helpful to have it in your formula sheet, okay? So just plug in that value, and I just found that through Google, 1.01 times 10 to the 5 pascals. Plus the density of fresh water, which I also found on Google. I don't think you'll be expected to memorize that, but it might be given to you on a test. So the density of fresh water is equal to 1,000 kilograms per cubic meter. Again, I found that on Google. So plus 1,000 kilograms per cubic meter, okay? And the gravity, constant gravity, is 9.81 meters per second squared. You'd probably already know that by now, but if not, again, add it to your cheat sheet. I think that's pretty important to know. And our depth in this case is, our H is 25 meters, right? Right here, 25 meters. That was given. So times 25 meters. Okay. And if I plug that all in the calculator, well, first of all, let's look at our units, right? So we've got 1.01 times 10 to the 5 pascals, plus we're going to get kilograms over meters squared, or kilograms over meter times second squared, right? And again, this is another thing to have in your cheat sheet, but the unit Pascal is equivalent to the unit kilograms meter per second squared, or kilograms per meter second squared. So these two are equivalent. They're interchangeable units, right? And if I multiply these values, I would get 245,250 kilograms per meter second squared. Okay. So since I know a Pascal and kilograms per meter second squared are interchangeable, I'm going to swap this guy with Pascal, since they're the same thing. Okay, so I've got 245,250 pascals. So I can add those guys together, and I would find that my initial absolute pressure, is 346,250 pascals. Okay, and I will highlight this in, I guess we'll use pink, just so it's easy to see. Okay, I have that. So I could use this initial pressure right here for this equation that we left off at earlier. And let's do that. Okay, because again, I know that my P1, right? I just solved it right here. P1. V1, that was given to us right here. 1 cubic millimeter right here. So we know that. P2, we do know because we know that the diver rises quickly from a depth of 25 meters, and we're being asked what the volume would be at the surface, right? So here at the surface of the freshwater lake, we're going to encounter atmospheric pressure, right? So this we know, right? Atmospheric pressure right here. So we know that, and we can solve for V2, which is what we're looking for. Okay. Okay. So again, copying this formula down here, P1 V1 equals P2 V2, right? And that's absolute pressure, initial volume, final absolute pressure, absolute final pressure, and final volume, okay? So let's plug and chug at this point. So we've got 346,250 pascals for P1. For V1, here we have 1.0 cubic millimeters. okay? Which, let's change that to, yeah, let's keep it at cubic millimeters. So 1.0 cubic millimeters, okay, is equal to P2, which, again, right here, P2 at the surface, that would be atmospheric pressure, which is right here. So is equal to 1.01 times 10 to the 5 pascals. And V2 is what we are looking for, okay? So at this point, it's just algebra, right? V2 is equal to 346,250 pascals multiplied by 1 cubic millimeter divided by atmospheric pressure, which is 1.01 times 10 to the 5 pascals. Okay? Our units would cancel out, Pascal and Pascal, and we would be left with the final volume is equal to 3.43 cubic millimeters. Okay, and that would be our final answer, which is, I believe that's what they were asking for, right? Yeah, the volume at the surface. Yep. So the volume at the surface would be this guy, 3.43 cubic millimeters. It's also asking us, assume the pressure difference is, does it seem that this difference is large enough to be a problem? Well, our initial volume was 1.0 cubic millimeters. Our final volume was 3.43 cubic millimeters, right? And that's about 350% larger volume for the nitrogen gas bubble in the diver's blood. So that's quite significant and would likely cause problems, okay? But as far as the final answer, that's our final volume at the surface.